All right, let's get started. So we're talking about similar triangles, and so it wants you to use a protractor to measure the missing angle of each triangle. Now, we've done this. I've done this a lot actually with these triangles, and I'm going to show you that this triangle, it's not a triangle, it is a triangle, but one of the angle measurements is wrong on it. And I want you to tell me which one. Sorry if you're watching on the video, you're not going to be able to see the board very clearly or at all. But I want you to tell me if you can tell which of the angle measurements is not the same. So remember, we did an IXL on how to use a protractor. Maybe if you're in the front row, you can read that. What does that angle measure for this triangle? Can you see it? What's it measure? Yeah, 30. Measures 30. It's definitely not 150, right? So we know you want to use the acute number. Yeah, it's 30-degree angle. Okay. What about this one? Can you read that in the front? What is it, Alexis? 60. Yeah, so they have it marked wrong. It is not a 50-degree angle. Can you go ahead and scratch out where it says 50 degrees and replace it with 60 degrees? And go ahead and do that for the next one because it's the same, has the same issue. All right, so we have one angle that's 30 degrees, one angle that's 60 degrees. Do I even need to measure the third angle? Why not? That's right. All triangles are going to add up to 180. So if you have an angle that's 30, an angle that's 60, what's the third angle have to be in order for all this to add up to 180? Got to be 90. Now, if I check this, use my protractor, it's pointing right there to the 90 degrees. Not only on that triangle, but on this triangle. Okay. So what we've proven, I'll just put a right angle box there. You guys okay with that? You know what that means, right? We've proven that these two triangles have the same angle measurements. Does that mean that they're the same triangle? No. Remember, if it's the same triangle, that means it's unique. Remember that word we said, a unique is one of a kind. So if we go back to our last section, we talked about unique triangles. Can you guys see these? If I give you the three sides of a triangle, and it actually can make a triangle, because remember that if you have one side that's just too long, you're not going to be able to make a triangle. So assuming that they do make a triangle, if I give you the three sides of a triangle, that triangle will be one of a kind. It'll be the only. So if I said, hey, make an 8, 9, and 10 triangle, all your triangles will look exactly the same. They'll all look like that one triangle because there's only one like it. But if I said make a triangle that has 30-degree angle, a 60-degree angle, and a 90-degree angle, do you see an A up here?
Question.
Is there an A? No, there's not. And so that's why that wouldn't be unique. If I said, draw me a triangle that has a 30, a 60, and a 90-degree angle, your triangle could be that big, or it could be that big. And sure, it's going to have the same shape, but it's not going to have the same size, most likely. And so it's not the same triangle. So if I had a question on my test that said, I'm going to give you these three angle measurements, and of course they have to add up to 180, otherwise you don't have a triangle. And I said, can you make one, many, or no triangles? The answer here would be many. You could all do as many different triangles as you want. They could all be 30, 60, and 90, just different sizes. We have a name for triangles like this. These are called similar triangles. Okay, similar. Similar figures, triangles, quadrilaterals, whatever they are, similar figures have the same shape, but not necessarily the same size. Now, what makes them have the same shape is that all the angles match up. You have the same angle measurements for each of the same angles in that triangle. Okay. In fact, that's one of the conditions we're going to see. Anytime two figures are similar, that means the corresponding. Now, corresponding is a new word for us. It means matching. Can you tell me which angle on the triangle on the right side matches with angle B? E. Okay, so you guys know what corresponding means then. Which angle matches with angle C? F. Okay, so that's what corresponds. So the corresponding angles, if they're similar, are going to be congruent. What's that word congruent mean? Equal size. Yep, equal size. So the corresponding angles are going to be congruent. What about the sides? If I told you two triangles are similar, are the side lengths going to be the same? Does it look like these two side lengths are the same? No, but something is actually special between those two sides. They're not equal, they're not congruent, but they are proportional. They are proportional. So we can set up a proportion to find what those missing sides are. Now, a while back ago, we did a worksheet called the triangle worksheet. Some of you guys remember this one because you didn't really like it. And I can see why, especially when you had so many different angles to find. The last two problems on the triangles worksheet gave you two triangles. It said they were similar and it asked you to find the missing side lengths. That was actually pretty easy to do. We could set up a proportion, or we could just figure out what that factor is that they're multiplying by. So to get from 3 to 12, they were timesing by what? 4. So, okay, what times 4 is going to give you a 20 then? 5 times 4. Yeah, so you can find, and that's exactly what we're going to do today. Except today, they won't be all that easy where we can just use mental math. We might actually have to use the proportion. Okay, some of them will be that easy. Some of them you'll look at and you're like, oh, that's just times by 2. Okay, some are like that. Some you can use mental math and some you have to rely on the proportion. Okay. All right. So these two things are true if your triangles are similar. The corresponding angles are going to be the same, congruent, and the corresponding sides are going to be proportional. So let's move into our first example. By the way, this little squiggly line right there means similar to. Shows you those two triangles are similar. Not the same size, but the same shape. All right. Example A says find X. Now, X is a missing angle measurement. Since we know the corresponding angles are the same, can you tell me which angle on the bottom triangle corresponds to angle X? Lucas, which one? The 50-degree angle. And since corresponding angle measurements are the same, that means X has to be the same size as the one it corresponds to, 50 degrees. That's easy enough. Now, example B, they've rotated the triangles. I need to find out what this angle is. And to find out what this angle is, I need to figure out which one it corresponds to. Be careful here. Lucas, you answered the last one. I'm going to let someone else answer this one. Which one do you, I bet it's not the right angle. Which one do you think, Frank? You are correct. It is the 65-degree angle. You know, it's got to be either the 65 or the 25. And so it comes down to, is it bigger or smaller? And so if you look at this angle is bigger or larger than what this one is. So it must match up with the 65-degree angle versus matching up with the 25-degree angle. They're both acute, but one's a little bit bigger than the other. So in similar triangles, the corresponding angles are going to be the same. The corresponding sides are going to be proportional. This is one where I'm going to have to use can't use mental math. I'm going to have to use the proportion. And here's why. Can you tell me what they multiplied 6 by to get to 9? It could have been a 0.5, right? It's not a whole number, I can tell you that. Okay, so here's what we're going to do. Instead of trying to figure that out, we're just going to say 6, I'm referring to this side right here, is to 9, that side right there. As now we have to go back to the first triangle, 8, which is the side here, is to X, which is this side here. And we have our proportion. We've solved a lot of proportions, even this year we have. I know you guys did some last year as well. When I'm solving a proportion, I use cross products. So I'm going to multiply 6 times X, which is just 6X. And I'm going to multiply 9 times 8. What's 9 times 8? 2. So I get this equation, and to solve that equation, I need to get rid of the 6 by dividing by 6. Maddox, what do you get for 72 divided by 6? 12. Nice job. Yep, and so this triangle actually has labels. All the sides are in meters. So we'll say 12 m, 12 meters. Simple enough. That's as hard as it gets today. Lainey, could you shut the door for me, please? Thank you. Let's move into the other triangle. Yes, Rayleigh?
Is this like what's going to be on the right side?
Yes. Yeah, you're going to have questions. So I believe the IXL is titled Finding Missing Angle Measurements and Side Lengths in Similar Triangles. It's a very lengthy name. It's a very easy IXL. It's going to have you questions like this where you have to, match up the corresponding angles, which are the same. And then it's going to have questions like this where you have to match up the corresponding sides and make a proportion out of them and solve it. Yes. Lucas already has it done. If that means anything to you. It doesn't mean much to me. All right. Example D. X matches up with which side on the other triangle? It matches up with the 9. The 6. It matches up with the 6. So that word matching, corresponding is what I probably should have said. It's the same definition, but that's the vocab word. So X and 6 match. Okay, what about the 6 on the left triangle? What's it match with? The 9 on the right triangle. And so I get this proportion here that I can cross multiply. I'm going to get 9x. And what's 6 times 6? 36. Can you divide by 9 and tell me what 36 divided by 9 is? 4. And we're measuring in what this problem? Feet, 4 feet. Okay. The 8 matches with which side on the other triangle? X on the other triangle, okay. And if 8 and X match up, I got to go back to the first triangle. I'm going to do 4, and what's 4 match up with? 6. Okay. So I cross multiply 4x. What's 8 times 6? 48. 48 divided by 4. Let's get 12 again. 12 what? 12 centimeters. Okay. And then the last one here is, I guess, a bit trickier just because it's been rotated a little bit. Let's see if you can use your heads to see which one is similar. Let's start with the X. Not similar, corresponding. Which side on the smaller triangle is X going to correspond to, Maddox? The 8. Good job. Yes, it just needs to be rotated back a little bit. So X is to 8 as, now this is where you're going to make a mistake. If you make a mistake, it's not, I mean, I guess you could make a typo in your calculator, but this is where your mistakes can be made. It's not going to be that you can't do the proportion. It's going to be that you set it up wrong. So be careful. If you do X is to 8, you can't do 5 to 9. If you started with the first triangle, you got to go back and do that first triangle again and put the 9 on top, just like you put the X on top. You can't do X on top and then put the 5 on top from the other triangle. You put the 9. So X matches with the 8 and then 9 matches with the 5. And it has to be in that order. Now you could flip both of them upside down. I got no problem with that, but you can't make it inconsistent. This one's going to give you 5X. And what's 9 times 8 again? 72. 72 divided by 5. Okay, so it's okay to not get a whole number. So you can get a fraction or a decimal answer, that's fine. This one doesn't have a label, I guess. We'll just leave it as 14.4. Okay, so you heard me say it, but I just want to prove to you, this is not the only way you could set up these proportions. Let's just go back to example C. I could have done, instead of doing 6 to 9, I could have done X is to 8 as 9 is to 6. That would have given me the same thing. If I do X is to 8 as 9 is to 6. And here's why that's the same thing. The X and the 6 are still diagonal from each other. So when I cross multiply, I still get 6X equals 72, which means I'm going to get 12 again. Here's another way you could do it, just to show you that you don't have to set up your proportion exactly like mine. What if instead of doing 6 is to 9, what if we did 6 is to 8? Stay on the same triangle. 6 is to 8. Now, if I do 6 and then 8, I have to do 9 and then x for my second one. Two completely different ratios, except the x and the 6 are still diagonal from each other, aren't they? The 9 and the 8 are still diagonal. So I can set up my ratio proportion different ways. As long as I'm doing it consistently, I'm still going to get the same answer everybody else gets. In fact, I bet you we could have solved example E a little bit quicker if we would have done the ratio I set up in the last one. So look at this. I know that you can't figure out what's 4 being multiplied, you get to 6. Okay, it's 1.5. You probably weren't thinking that. What's 4 being multiplied to get to 8? What's 6 times 2? We could have used mental math on this one. So as you're doing your IXL, there could be quite a few problems, quite a few triangles you're looking at that you could just get away with using mental math, which is why I'm not going to assign you or make you turn in a work paper for this IXL. Okay. So first of all, everyone's work papers look extremely different. But yeah, you could have problems like this that you don't have to show any work on. You could definitely get away with not showing any work on problems like this, where you just have to find the missing angle measurement. There's no work there to show, right? But if you get a problem like example C, you might want to have a scrap sheet of paper handy so you can do the calculations. I know the IXL app lets you write on the app. It's not very smooth when you do that. Maybe you use Notability and split screen it, but yeah, you can write a proportion out if you need to. If you don't need to, you can use mental math. That's fine as well. All right, let's get to the important part of the lesson. Like, why would I need to be able to use similar figures? Because we use similar figures with indirect measurements. So there's our next vocab word. Indirect measurement uses similar figures to find missing measures, or finding a missing measure, like an angle measurement or a more particular side length, okay, when it's difficult to find them directly, meaning it's difficult to measure them directly. Now, we're actually going to go outside when it warms up and nice sunny day. We'll go outside and we'll measure how tall that flagpole is out there, not flagpole, light pole. Flagpole's in this question, the light pole. But we're not going to climb to the top of the light pole to measure it. What we're going to do is we'll use indirect measurement and we'll use proportions the same way we use proportions on these triangles right here. Okay, so there's an example we'll get to in a second that actually is very similar to what we're going to do. Okay, we'll go out and do that once the weather's nicer. It'll have to be during one of our success times because it's still usually kind of dark in the morning, although it has been getting lighter out. But yeah, we'll pick a nice day to do that during one of our success times. All right, so this next problem says, we're going to use indirect measurement. You plan to cross a river and you want to know how far it is to the other side. Now, it'd be very difficult to measure how far it is to the other side without swimming it with like a rope attached or a tape measure attached to your back or something like that. So what they've done is they've roped off or marked off some different measurements here, which I'm not sure how they calculated. I'm just going to go ahead and say, I'll take their word for it. It says, explain why the two triangles are similar. So they are similar. Explain why they are similar. And then what's the distance x across the river? How far is it across the river? Let's talk about why they're similar first. We said that if you can prove that all 3 angle measurements are the same, then you're going to have 2 similar triangles. Let me rephrase that. I shouldn't have said all 3 angle measurements. If you can prove that there are 3 sets of angle measurements, it's probably a better way of saying that, then you can prove the triangles are similar. So I need to match up 3 sets of angles. And if that's true, then it'll be proportional. The side lengths will. I can see right now 1 set of angle measurements that already matches up. Do you see the 2 angles that match up? Which ones, Alexis? That's exactly right. The 2 right angles are going to match up. They're both 90 degrees. Okay, so there's 1. I need 3. What about this angle here and this angle there? Are they the same? Why are they the same? What kind of angles are these when they're opposite from each other? Frank? Vertical angles, you remember that was like our very first vocab word. Vertical angles are congruent. So now we have two sets. Now it comes down to our last set, angle A and angle D. Okay, here's what we know. Do you remember on our first problem? Let me get rid of the lines. When we recalculated and said that was a 60-degree angle, we knew the other one was 30 degrees. Did we have to measure the last angle? You knew it was 90, didn't you? Because all angles in a triangle have to add up to what? 180. So if we already know that two angles are the same, doesn't that last angle have to match up with the other one to make it all add up to 180 for both triangles? If this is 90 degrees, didn't it force this angle to also be 90 degrees? I mean, doesn't 30, 60 plus 90 equal 180? And again, 30, 60 plus 90 equal 180. So there's a theorem that you guys will talk more about next year. Well, I'm introducing it this year though. You need all three angles to match up, but if you can prove two of them match up, the third pair automatically matches up. So these angles here, angle A and angle D, they have to match up. I don't know what I know this is 90. I don't know what the vertical angle is, but I know that this plus the vertical angle has to add up to 90 because that plus 90 equals 180. And I know that for the same reason, that angle and that angle has to add up to 90 to force that angle with 90 to be added up to 180 for those triangles. So I can prove that the missing set is congruent. And so I have two similar triangles. And now that I know they're similar, their side lengths are going to be proportional. And I can solve for X. Okay. I'm just going to write 50 down. You have to start somewhere. 50 feet is this side length right here. Can you tell me what side length on the bottom triangle the 50-foot side length corresponds to? Alexis? It's the 40. Nice job. The 50 has to correspond to the 40. And it's actually really easy to tell since I put the arc marks in. The 50-foot side is between the right angle and the one arc angle. The 40-foot side is between the right angle and the one arc angle. So 50 matches up with 40. If 50 matches with 40, go back to the first triangle. What's 60 have to match with? X. And we can cross multiply. And I'm not sure why I put my proportion down there. There's no room to work. I'm going to put it back up here. All right, cross multiply. 50 times X is 50X. What's 40 times 60? 2,400. Divide that by 50. How far is it across the river? 48 what? Feet. 48 feet across the river. And we didn't actually have to measure that side of the triangle. We just used proportion. That's called using indirect measurement. Now, this is very similar to what we're going to do when it gets, nice and sunny out, because when it's sunny out, the sun's rays, assuming that sun's outside, the sun's rays are actually going to be parallel to each other, forming the third side of our triangle. One side being the height of us, and then our shadow is the base. And then one side being the height of the flagpole, and then its shadow. Now, we're not going to know how tall the flagpole is, but if the sun's rays make this similar triangles, then I can set up a proportion. And so here's what my proportion would look like. How tall is the person? 5 feet. How tall is the flagpole? X. Good. Go back to the person. How long is their shadow? 3 feet. Go back to the flagpole. How long is its shadow? 36. There's my proportion. Cross multiply. 3 times X. What is 5 times 36, Hunter? 180. Divide that by 3. 60. There we go. The flagpole pole is 60 feet is a really tall flagpole, actually. And you know what? I don't think there's no way this is drawn to scale. Because if this dude's 5 feet tall, then that's 10 feet tall, and that's 15 feet tall. I don't even think the flagpole looks to be 20 feet tall, so I'm guessing that this is not drawn to scale. Now, there are flagpoles that are tall. I've driven through, especially like you can drive through like on the interstate. There's, forget where it is in Indianapolis. They have this really big American flag that you can see flying. But I'm sure there are flagpoles that are much taller than that too. But yeah, that's not drawn to scale. Okay, let's do this one here. Oh, it's Parker's problem. Still stuck in California. All right, so let's start with H. H is the height of the palm tree. What's the height of the person? 6. Okay, go back to the palm tree. What's its shadow length? 15. What's the shadow of the person? 3. Cross multiply, 3H. What is 6 times 15? 90. And Sierra, what's 90 divided by 3? Yep, 30, and then this would be measured in feet again. Could I have done that without having to use a proportion? Could mental math have worked? It could have on this one. Now, could you tell that they were timesing by 5 to get 3 to 15? So 6 times 5 gives you what? Gives you 30. You could use mental math. Or how about this one? This is even easier. What did they times 3 by to get to 6? 2. What's 15 times 2? If you can use mental math, that'll save you some time. If you can't use mental math, because mental math doesn't work on every problem, go ahead and use your proportion. Or you could just use the proportion anyway. It's not very difficult to do. All right, we got one last problem. Determine which triangle is not similar to the others. How can you tell? Remember, similar means they have the same shape, but not necessarily the same size. These all look to have the same shape. Do they? Lainey? Yes. The blue one. What's wrong with the blue one, Lainey? You're exactly right. So the definition of similar, same shape, different size, that's great unless you can't tell if they're the same shape. That triangle, although it looks to have the same shape, is not, because as Lainey pointed out, the angle measurements are different. So it's not quite the same shape. It's close, but not quite. You're exactly right. That triangle does not belong with the other 3. If it were similar, its corresponding angle measurements would all have to be the same. Notice that angle B, F, and H, or sorry, B, E, and H are all 82, and then K is 85. Yeah, it doesn't work. Or as Lainey pointed out, 35 doesn't match with 32, so that doesn't work either. If the angle measurements, if the corresponding angle measurements aren't congruent, the triangles aren't similar. What about their side lengths? Are their side lengths going to be proportional? If the triangles aren't similar? Nope, they won't be proportional. So we wouldn't be able to do what we just did with the palm tree problem, for example. All right, that's it. Your IXL is your homework tonight. 8th grade, don't do 7th grade S.6 because I won't count for anything. 8th grade S.6 is your homework.